Okay, thanks a lot. Good morning, everyone, to the first session. I hope you enjoyed your dinner. My name is Frederik Arnknecht. I have the pleasure to be the session chair of the crypto session this morning. So we are I'm expecting 6 interesting talks this morning. Before we're going to start, 2 requests, one for the presenters and one for the audience. Starting with the audience, if you have questions, please post these into Zulip. That just makes it easier to organize the Q&A session at the end of the talk. And speaking of the Q&A session, so this is my request to the presenters. While we're taking the questions of one talk, please, the speaker of the next talk, come already to the desk so that we can set up everything so that we stay in time. Okay, so staying in time is exactly 9 o'clock, so we can start with the first talk entitled An Efficient Data-Independent Priority Queue and its Application to Dark Pools. Sahar is giving the talk, and the stage is yours.
Good morning, everyone, and thanks for joining us this morning for our talk. So as I mentioned, the title is An Efficient Data-Independent Priority Queue and its Application to Dark Pools. You might not haven't heard about any of these terms like the data-independent or dark pools, but in a nutshell, this talk will be about a real-world application of cryptography, especially into finance. And you will see actually how we can apply it. And it's a joint work with my great colleagues at AI Research Lab at JP Morgan, Algo Crypt Center of Excellence. So how the trades happening in the financial market, in a simple words, is basically someone is going to sell some of the stocks that they have, some of the securities that they have. So, for example, the stock XYZ going to be sold with the 50 number of shares at the price 99, and we have a buyer actually that is going to buy the same stock with the amount of 60 number of shares and with the price $101. So usually these type of trades happen in the public exchange market, for example, this NASDAQ or a New York Stock Exchange. And it actually goes through a mechanism called double auction mechanism, which basically means that all the orders buy and sell come in to this public exchange in clear, and everybody can see that in public. And this market venue, this market exchange platform, does the basically matching between these sellers and the buyers. And the match happens in the sense that if the buyer is going to, basically buyers usually come with a price that is the maximum price that they can afford to buy something. And the sellers actually come with the lowest price that they are willing to make that trade happen. So if the buyer's price is more than a seller's price, in this case, we will have a match. Otherwise, in the opposite direction, we would not have a match. So that's actually what happens in real world stock market exchange in public. But as you can see, there are problems here. So the main drawback is the privacy of the basically participant in this market, because everything can be seen in clear to the public. And if you can imagine, we have some large players. For example, someone wants to sell or buy a number of shares in a number of thousands or millions. So they would have a real huge impact on the market, and it will change the price of the market significantly. So because of these problems, they actually decided to move these large players into a private exchange, which is an alternative exchange platform called dark pools. And as the name suggests, dark pool means that everything is kind of like in dark. So people, sellers and buyers, for example, wants to, in this case, sellers selling 50,000 number of this share, and the buyer is willing to buy 60,000 of that share, but they don't really know the price of this exchange happening on their net, because only the dark pool and the operators of the dark pool can have access to this data, and everything is basically hidden from the public. So as you can see, we are reducing the impact that these large players would have on the market, but at the same time, we are actually exposing those private information to the dark pool operators. So as you can imagine, these dark pool operators, because they are the only ones can have access to this very important and sensitive data, they could have some attacks. Basically, for example, there's a famous attack called front-running attack, which they could put their orders when they see that there is a large basically client coming in, so they can push their orders in front of them to benefit from this change in the market. Or, for example, they can buy cheaper, sell it higher, and make profit in between. And as a real, basically, world problem that they created, so in 2016, some of the firms collectively had to pay this amount of like $150 million to settle some cases for this problem. So there is usually the mistrust and the conflict of interest problem in these dark pools. So in this talk, I'm going to tell you how we can use cryptography actually as a basically solution to provide privacy and security for the clients or for the people that are participating in the dark pools. So as we call it, privacy-preserving dark pool, it's a mechanism that eliminates the need for the traders to trust a single operator of the dark pool. And in that case, sellers and buyers interact with each other basically through the operator without exposing in the clear their volumes of their trade or the price of their trade, which basically we are using cryptography solutions. And you have to, basically very important to mention that because of the increase of interest into these privacy-preserving solutions, we have one example of somewhat similar to this problem, which is doing the portfolio matching of the clients. It's called Prime Match, only matching the volumes of the clients. It's published in Usenet 2000 and this year, 23, and it's now in real production at JP Morgan. So clients are actually using it. So there are two ways that we can apply cryptography for privacy-preserving dark pools. One of them could be using homomorphic encryption, which, as many of you have heard, it's a very expensive solution. I have some slides for that, but I wouldn't go to that because of the lack of time. We implemented this solution as well. We have comparisons in the paper. But the one that I'm going to focus on, which is more efficient, is basically using MPC for this application, for this problem. So the MPC, might you have heard about, it's multi-party computation, which basically enables multiple parties to compute a functionality on their private data without revealing their private data to each other or to the public. So that's how, the magic behind MPC. But how it's going to be used is basically, I have to mention before that using multiple parties in the real world, in the basically clear, is also something that came to practice by motivated by this turquoise plateau market, which is actually something happening in Europe, done by London Stock Exchange, and JP Morgan is also one of the partners into basically this multi-party dark pools to eliminate that single point of trust and failure. But it's without cryptography. So let's imagine if we want to bring cryptography into that, is basically what we do. All the sellers and the buyers encrypt their orders, whatever they're basically going to would be the volume and the price of the order. We are not hiding in this basically problem the direction of their selling or buying, only the price and the volume. So they send everything encrypted to this multiple party platform, and then what they receive is basically the result if there is any match or no match, which basically no one else except those clients can actually decrypt those messages. So let me actually walk you through a simple example of what is actually happening really in any of these in clear or in the basically encrypted version of this dark pool or a stock market. So imagine we have an order book. It's an order book is basically consists of the orders that hasn't been satisfied. So when an order comes in and if there is no match for that, so that order should be put into the queue in the order book, waiting for the new incomings to basically hopefully to be matched in the future. But so imagine we have an order book. These are the orders that are not having been matched. So as you can see, the top part, which is in green, they are the sell orders, and they are, as if you can imagine, this middle line would be the top of the queue for each of them. So the sell orders are sorted ascendingly. Basically, the price, the minimum would be at the top of the queue. For the buy orders, the maximum price would be on the top of the queue, because as we mentioned, the buyer is going to put the maximum amount that they're willing to pay, they can afford to pay, and the sellers should put the minimum that they can accept that basically transaction to happen. So having this in mind, as you can see, these prices doesn't match, so that's why these actually orders are still waiting in the order book. So imagine one order comes in, it's a buy order. So this buy order, for this matching this buy order, we go through each of these sell orders from the top of the queue, okay? And since the price matches, basically the price of the buy is more than the price of the sell, so there is a match, and what basically happens is basically we have to update the book because it was only 60 number of the shares the buyer was willing to basically buy. So we have to update the number of volume that for the sell in the order book. So as you can see, it's 60, like 200 minus 60 would be 140. And so if the buy order comes in and the price is less than basically what it's supposed to be matched with any of them, so there is no match. And what happens is that order should be going into the buy order book, which basically, as you can see, there would be multiple comparisons and an insertion thing. So imagine if we are going to do everything in cryptography, encrypted, which will require secure comparisons, which basically is known to be a very expensive operation. As a solution, we decided to basically design this secure dark pool with a data structure that makes it faster. This data structure could be a priority queue, which is the priority is based on the price, and it's going to be data independent, meaning that we don't need to do comparisons as many as we needed to basically to do for the priority queues. So the idea of this priority, data independent priority, came from the work by the Taft at 2011, which basically could provide some operations like insert and extract front. And as I mentioned, this is data independent, so it means that there is no branching required because it doesn't depend on the input data. And it's basically, there are some magical algorithms behind that, but basically we mentioned in the paper. So what we needed to basically do, but we had to modify these operations in order to make it more work for our dark pool, privacy-preserving dark pool, and we had to modify the data structure in the sense that we could afford to do that read front operation. So we need that read front operation because we need to read from the top of the queue without extracting it. Because if we extract it and there is no match, so we have to insert it back to the queue, which incurs a lot of comparisons and a lot of cost for us. So we needed to design this operation to make it basically improve the time. So these are the results that we achieved for having the independent priority queue, data independent priority queue. We basically was able to add this operation of read front operation with no required comparison. We reduced the number of comparisons in all of the operations, especially we actually have the zero amortized cost for deletion. And by applying that data-independent priority queue into our privacy-preserving dark pool, we reduced the cost of operations from the linear to full logarithmic. So if you remember, I mentioned we have to do insertion, secure insertion into the queue if there is no such a priority queue, which is a linear operations. So now we reduce it to full logarithmic operations. And based on the implementation that we did end-to-end, everything that's basically implemented from scratch. So we could improve the result of the previous works by 200 to 400 times. And we did basically implementation for the three-party honest majority with one malicious adversary. And these are the summary of our results. Just pointing out to those red boxes to mention that the top part is the MPC solution without using data-independent priority queue. The bottom one is our solution with the data-independent priority queue and MPC. The right one shows that we could actually run this algorithm for large number of orders. For example, you can see at the bottom it is we are fulfilling almost 1,024 number of shares. So as a summary, we provide a solution that basically merging multi-party computation, which is one of the branches of the cryptography, with the novel data structure to provide more efficient data independent privacy-preserving dark pools. And this dark pool operations, this data-independent priority queue data structure is very interesting and can be used in any applications that we need to do some expensive sorts. So with that, I'm concluding my talk and can refer to the paper and the ePrint or to the proceedings for the pets. Thank you so much for your attention.
Yeah, thanks a lot. One question has been uploaded or posted to Sulip. Let me just read it out. If the direction of the order is not encrypted, then does that not leak information about the demand of the stock?
So can you read the last part of it? Leaking about?
So if the direction of the order is not encrypted, then does that not leak information about the demand of the stock?
So basically, we are affording. So in our scenario, we are considering that leakage is actually like it's allowable. So we allow the attacker to learn the direction, but it doesn't tell anything about the price or the number of shares that they're going to. But there are actually we can actually like extend this work to cover also the direction as well.
Good. And I think we have time for one short question. Can you think of other applications as dark pools?
Like besides dark pools?
Yeah, besides dark pools.
So as I mentioned, so this solution could be used any like secure sorting, for example, somewhere that we need to do a lot of comparisons. So this data independent priority is interesting because it removes the need to have more comparisons. So I could think of like one of the examples I mentioned, we are going to actually incorporate this data independent priority queue into the prime match operation that we have. Is basically matching the portfolio of the clients.
Okay, I think time is over. Thanks a lot.